We have taken a look at what happens when you take limits at infinity of polynomial function, and the answer ends up being positive infinity or negative infinity based on the end behavior of your polynomial. Now we're going to take a look at limits at infinity of other types of function, and specifically what happens when you take the limits at infinity and it ends up being a number. So we have this mathematical definition here. Let's read it together. If the values of the function f of x approaches the number L as x increases without bound, we write the following notation, and it reads as the limit as x goes to positive infinity, f of x, is equal to L. And similarly, we would write the limit as x goes to negative infinity of f of x is equal to m if the functional values f of x approach m as x decreases without bound. In this situation, if this behavior occur, y equals L and y equals M are called horizontal asymptotes. And so there's a nice little diagram that shows this, right? X increases without bound and it's getting closer and closer to the line y equals L, which is the top line. And then as x goes to negative infinity, it's getting closer and closer to the line y equals m. So if you know that this behavior is happening, you have a horizontal asymptote, or vice versa. If you have a horizontal asymptote, you know that these behavior have to occur. So I'm going to draw four possibilities of what happens when you have a horizontal asymptote, because right, we will be using this when we graph later in calculus. So I'm going to draw a hypothetical horizontal asymptote. And again, you learned this in algebra, but now we can actually talk about it when it comes to limits. So there are four possibilities. Either x is increasing without bound, which means it's going to infinity, and your function is approaching the horizontal asymptote from the top, or it's increasing without bound and it's approaching the asymptote from the bottom, or it's decreasing without bound and it approaches the asymptote from the bottom, or it's decreasing without bound and it's approaching the asymptote from the top. Now, when you have a horizontal asymptote, you know at least one of these has to happen, and two can happen together as long as the function still passes the vertical line test. Okay, so on top of that, another concept we're going to use is called the reciprocal limits. And so you have that if p is a positive real number and k is any real number except for 0, you have these two limits that are really good if you remember them. And they're easy to understand. The first one is the limit as x goes to infinity of k over x to the p is equal to 0. And then you have the limit as x goes to negative infinity of k over x to the p is also equal to 0. And just think about this, right? If we think about the first one, we have a constant at the top of the fraction that doesn't change. And then we have the bottom, we have an x to a power, and we're putting in numbers for x that's getting really, really, really large. So the denominator of the fraction is getting larger and larger and larger. And when that happens, your fraction gets smaller and smaller and smaller, so it's approaching 0. And the same kind of concept goes for the second one. So what we're going to do here actually is we're going to take the limits at infinity for rational functions. So keep in mind, right, it's important for you to know is that 2x squared plus 3x plus 1 over 3x squared minus 5x plus 2 is a rational function. It's a polynomial divided by a polynomial. So we're taking the limit as x goes to positive infinity. So we're going to be plugging in larger and larger and larger numbers for x. When this happens, this little tail here at the end, because you have 2x squared over 3x squared, the numbers when you square them are going to become so much smaller than when you just have x to the first power. So as the number gets extremely large, the squared part overpowers the rest of the tail, I like to call it. So actually what you want to take a look at is you just want to take a look at the part of the numerator and the denominator that has the highest power. We call it the degree of the polynomial. So what that's going to give us is it's going to give us the limit as x goes to positive infinity of 2x squared over 3x squared. But what happens here is that the x squared actually cancels each other out, and we have the limit as x goes to infinity, positive infinity, of 2/3, which is just going to be 2/3 all right? Because the powers are the same. It's the same at the top and it's the same at the bottom. So what ends up happening is when you plug in a really large x and you square it, it's going to end up canceling each other out. Now keep in mind again that you are not the you are approaching 2/3. So as your x's are getting bigger and bigger, your y's are going to get closer and closer to the number 2/3. It will never be 2/3, but it will get closer to the number 2/3. So what happens here is you have a horizontal asymptote at this rational function. So y equals to 2/3 would be the horizontal asymptote of your function. Okay? Okay, let's do another one like this. So you have the limit as x goes to negative infinity now of this function. So again, you want to look at the degree, the highest power of the numerator, which is 3x cubed. And you want to look at the highest power in the denominator, which is x to the fourth. And the tail of it, as the numbers go to negative infinity, won't affect the function as much as cubing it into the fourth. So what we end up having is we have the limit as x goes to negative infinity of 3x cubed over x to the fourth. But again, things canceled here, right? I have 3 at the top and I'll be left with 1 at the bottom. And so this gives me the limit as x goes to negative infinity of 3 over x, but from the reciprocal limit rule, we know that this is going to be 0, all right? Now, the reason for that is because, again, the power of the denominator is greater than the power in the numerator. So when you put something to the fourth, it's going to make that so much more intense than at the top of the fraction. So it's going to make the fraction approach 0. So for this graph, 3x cubed minus 6 over x to the fourth minus 5x squared plus 1, that graph would have a horizontal asymptote at y is equal to 0. So we're going to put the concept of horizontal and vertical asymptotes together. Now remember that a horizontal asymptote happens if as x goes to positive or negative infinity, your y's are approaching a number, and the vertical asymptote is the opposite. If x is approaching a number and your y's are going to positive or negative infinity, then you will have a vertical asymptote. So let's do the horizontal ones first because we just did it on the previous page. So we want to take a look at, let's erase it, the limit as x goes to infinity of our function x squared minus 9 over x squared minus 4. But again, here you have the degree of the top and the degree of the bottom. So we will have the limit as x goes to infinity of x squared over x squared, which cancels each other out. And that will give us the limit as x goes to infinity, of 1. And so that will just be 1. Okay. Now, if similarly, if I put negative infinity because the x squared and the x squared cancel each other out, you will still get 1. So you will have a horizontal asymptote at y is equal to 1. Now, the vertical asymptote will come from the behavior of the zeros in the denominator of your function. So to be able to find the zeros, we need to factor our function. So we have f of x is equal to x minus 3 over x plus 3 over x minus 4 times x plus 4, x minus 2, I'm sorry, times x plus 2. So none of the factors at the top are going to cancel with the factors at the bottom. So we have 2 zeros in the denominator. We have 2 and negative 2. And because the factors here do not cancel with the zeros from the top of the function, both of these are going to be vertical asymptote. And we see that by taking the limit. We have the limit as x goes to 2 of f of x. And if you do a table for this, right? And you want to, now here, this is the part where you have to figure out, okay, is it going to go to infinity or is it going to go to negative infinity? And so you want to think as you're taking numbers from the left of 2 and from the right of 2. So you could create a table, right? You could plug in some values for that. And what's going to happen here actually is that you are going to get a negative infinity here. So I'm sorry, we have first from the left, I should say. right? So you would take the limit as x goes to 2 from the left, and that's going to give you a positive infinity. Apologies. And then you have the limit. And again, you could do the table on your own since we've already done this before. I'm not going to take the time here to do it. And this is actually going to give you a negative infinity. Okay. And then, so the limit here would not exist. One would be positive infinity, the other one would be negative infinity. And you could do the same thing for negative 2 from the left. And again, if you do your table, you will see that the numbers will get larger in the positive direction. And then you have the limit as x goes to negative into, from the right of f of x. And you're going to see that this is going to be negative infinity. So because of this, you know that this behavior, it shows you, it solidifies the fact that this is a vertical asymptote, right? This has to happen if it's a vertical asymptote, so you want to check that. And so you have a vertical asymptote at 2 and at negative 2. Okay, so here just again take a note at the difference, right? The horizontal asymptote is as x goes to infinity or negative infinity, and it approaches a number, and a vertical asymptote, it's the y's going to infinity or negative infinity. Okay, now we want to take a look at an example where we're finding the limits graphically of infinity and negative infinity, and also a number, kind of putting everything together about limits. So first we have the limit as x goes to negative infinity. It's decreasing without bound. So you want to take a look at this portion of the graph. Oop, that was a horrible, right here. So as your x's are going in this direction, you want to take a look at the behavior of your y. And the behavior of your y is that as x is getting smaller and smaller in the negative direction, your y's are getting closer and closer to 0. Okay, so it means that there's a horizontal asymptote there. So this will be 0. Then if you take a look at as x goes to infinity, now you're looking here, right? Your x's are going to the positive direction. Your y's are approaching the number 1 because there's a horizontal asymptote there. So this would be equal to 1. And then you have two examples from previously about limits. So you have the limit as x approaches 2 from the left. So remember, this is 2 here. So if we're approaching 2 from the left, we want to take a look at this part of the graph. So your graph is shooting down, which means that you're going to negative infinity. And if you're approaching from the right, you want to look at this part of the graph, and that's going to infinity. So this is a visual representation of horizontal asymptotes versus a vertical asymptote. All right, and then to end, we have an application problem. So a company manufacturing surfboards has fixed cost of $300 per day and total costs of $5,100 per day for a daily output of 20 boards. Assuming the total cost per day is linearly related to the total output of surfboards per day, X, okay, so X represents the total output of the surfboards, write an equation for the cost function. So it's telling you that the cost function is linear. So let's start off with that. So we have part A. Okay, so let's remember that linearly means that you have y is equal to mx plus b. Now, you have a fixed cost of $300 per day. So that's the part that's fixed, right? That's your B. It's never going to change no matter how many boards you have. So even if you didn't manufacture any boards, you would still have a fixed cost per day of 300. That could be, right, the part of the rent of where your warehouse is and so on. Okay, it doesn't matter how many you make. While the changing cost would be the material that you're using and so on. So far we have y is equal to mx plus 300. We know that when we output 20 surfboards, input 20, we output 5,100 in costs. So my input is my x, that's this amount of surfboards, and then we output the 5,100. So using this, right, remember input x, output y, we can find m, we can find the changing part of the function here. So we have 5,100 is equal to 20m plus 300. So we'll subtract 300, which will give us 4800 is equal to 20m, which means that m is going to give us 4800 divided by 20, which will give us 240. So our cost function is going to be y is equal to 240x plus 300. And you could see, right, if you input 20, you would get back 5100. And we know that it's linear, right? That was the key word, so we're able to use mx plus b. And of course, more appropriately, you want to use c of x is equal to 240x plus 300. Okay, that's part A. Part B. The average cost per board is given by, and so this is always the average cost function. It's your total cost divided by your how many, in this case, surfboards you have. Okay, that will be your average cost. And that makes sense, right? Because if you have 5 people in a room and you want to find their average age, you add up all their ages and you divide by 5. So we have that the average cost is going to be our cost function, which we have from the previous part, 240x plus 300 over x. Done. Okay, part C. We want to sketch the graph of the average cost function, including any asymptotes from 1 to 30. Okay, so because we're going from 1 to 30, the first thing that would be a good thing to do would be to find what the average cost is at 1 and at 30. So we have average cost of 1 is going to be 240 times 1 plus 300 over 1, so that will give us 540. And then we're going to have the average cost at 30 surfboards. It's going to be 240 times 30 plus 300 over 30. And I will let you do that on your own, and that's going to give you 250. Okay, so we want to make sure that we include any of the asymptotes that might be there. So again, we want to do what we did in one of the previous problems above. So we have the limit as x goes to, and again, I'm going to take positive and negative infinity at the same time here, because you're going to see that they're both going to be the same. 240x plus 300 over x. We want to look at the part with the highest power in the top and of the bottom. So as the numbers get increase without bound or decrease without bound, the 300 will become more and more, it won't matter as much, okay, to the point where it will barely make a dent as the numbers get really, really large or very, very small. So we have 240x over x, but the x's cancel out. So we have the limit as x goes to positive or negative infinity of 240 is just 240. In this case, we didn't even really need to take to negative infinity because your x's can't be negative. All right, but I just wanted to show you an example of both. So what that means is we have a horizontal asymptote at 240. Now, our other asymptote, our vertical asymptote, will come from the bottom where it makes it 0. So I'll write the function here one more time to remind ourselves. So it's 240x plus 300 over x. And the bottom and the top are already factored, so x equals 0 will be the 0 of the denominator. So we have that the limit as x approaches, and in this case it would only be 0 from the right, because again, you can't have negative x's, and you are going to have 240x plus 300 over x, and you would create a table for this, which I'll let you do on your own, and you will see that it will go to infinity. Okay, so we're going to use all of this to help us graph. So we have a vertical asymptote at x equals 0. We have a horizontal asymptote at 240. Right, so this is y is equal to 240. And then we have 1 here and we have 30 here. And when we put in 1, we got about 540. And when we put in 30, we got 250. And so from 1 to 30, our graph would look like this. Okay, and our last part is what is the behavior of the average cost per board as production increases? Well, we already found this out because we actually already did it right here. Oops, let me circle. Right, as your production is increasing, which now you can visually see with the graph, the behavior is that your average cost is approaching 240 degrees. Okay, so your average cost approaches $240 as production, oops, increases. And so here's an application problem.